In this video, we're going to consider a new kind of equation using exponents. Let's start with a bit of review. If we have 2 to the first power, this means we're multiplying 2 one time, so we're going to get 2. If we have 2 to the second power, or 2 squared, that's 2 multiplied 2 times, and we're going to get 4. We can continue that process, 2 to the third. This is multiplying 2 3 times, so 2 times 2 times 2, which gives us 8. And you can see that each time our exponent increases by 1, our answer multiplies by 2. Because each time we're just multiplying by 1 more 2. So 2 to the fourth power would give us 8 times 2, or 16. And if you consider our exponent as an input, and our answer here as an output, we can create a new kind of equation. We can say that 2 to some power x equals some answer y. And if we reverse the order, we would get y equals 2 to the x. So this is our new type of equation. We call it an exponential equation because our input is going to be an exponent. And as we saw above, each time we increase x by 1, y increases by a multiple of 2. So this is different from linear equations. When we looked at those, we saw that each time we increased x by 1, y increased or decreased by the same number. With exponential equations, y is going to increase or decrease by a multiple of a number. Let's try to visualize this. So if we had a line, each time our x increased by 1, y would go up by the same number. And because y increases by the same amount each time, we call this constant growth. You can also think of it as steady growth. And if we consider our new equation, the exponential equation, things change quite a bit. You might notice that we have kind of made an xy table over here. The purple numbers are the x values, and the orange numbers are the y values. So we can plot each of those as a point. The first point, x equals 1, y equals 2. Then x equals 2, y equals 4. Now we're going to need more space on our y-axis. So our next point is x equals 3, y equals 8. And our final point is x equals 4, y equals 16. And if we connect our dots, we'll get a curve that looks like this. This is an exponential curve. And since the y values are getting bigger and bigger, we say this is exponential growth. We can also have an exponential curve where the y values get smaller and smaller. And we'd refer to this case as exponential decline. When we talk about exponential curves, a common word you'll hear is rapid. Exponential curves grow or decline rapidly, as opposed to our line, which is going to have steady, constant growth. And you can also refer to constant growth as linear growth. You'll hear these different terms to describe a curve. If you hear that the curve is growing rapidly, that's going to be exponential. If you hear that there's a steady or linear growth, that's going to refer to a line. And you might be wondering what this section here means. What does it mean when x equals 0 or a negative number? Let's go back to our example on the left. If x equals 0, we're going to have 2 to the 0th power. Now, what does it mean to multiply 2 0 times? It doesn't mean anything. It has absolutely no meaning. You can only multiply 2 1 or more times, but what we noticed here is that there's a pattern. Each time x increases by 1, we're multiplying the y value by 2. So we're just multiplying by 2 again and again. Another way to think about it is if we go backwards, going from x equals 3 to 2 to 1, we're actually dividing by 2 each time. So if we start at 2 and then divide by 2 one more time, we're going to get 1. So we say that 2 to the 0th power equals 1. We call this extending the definition. Exponents only make sense for positive values, but now we're extending the definition to include 0 and negative. And we extend that definition by just continuing that pattern. So if we wanted to find 2 to the negative 1 power, we'd start with our 1 and then divide by 2. 1 divided by 2 is 1/2. Again, you cannot multiply 2 negative 1 times. That has absolutely no meaning. However, extending the definition allows us to fill in this part of the curve. And why is that useful? Well, as you've seen in word problems, we can use equations to represent real-world situations. For example, let's say that our x-axis represents years. So 1, 2, 3, 4 represents 2021, 2022, and so on. And our y-axis represents how much money a company makes in millions of dollars. So 1 million, 2 million, and so on. That would mean that x equals 0 would allow us to estimate how much money the company made in 2020. And if we go back another year, we can estimate how much money was made in 2019. So extending the definition to 0 and negative numbers is useful in real-world situations for making estimations. So in this case, we don't have information about 2020 and before, and we can estimate it using this exponential curve. That's the same thing we would do with a linear equation. For example, if we only had 4 points of data for this line, we could find the equation of that line and then make an estimate for an x value down here. We'd plug that into our equation, and that would give us another point. In this course, we focused on linear equations, quadratic equations, and now exponential equations. And in each of these cases, we've seen that math that seems kind of useless at first turns out to be very useful in helping us understand more about the world. And as you take classes in chemistry, biology, physics, economics, finance, you'll see more and more equations that help us better understand situations in the world. Even the most abstract kinds of math eventually find their way into real-world application. It's definitely something to appreciate.